Hi everyone, this is Dr. Black from BW Learning, and together with Dr. White, we are going to share with you videos on engineering related modules, science, and mathematics to help students understand the concepts better. So for our first video, I'm going to share with you on the first law of thermodynamics. Well, when I came across this topic, students are actually asking me, what is the temperature of the system in the question? How to determine pressure? What is the heat transfer? Why do I need to find the work done? What is the enthalpy of the system? Why do we need the internal energy? And how does volume affect the system? So today, let's find out. Thermodynamics helps us to understand the fundamentals behind air conditioning and refrigerator. It also helps us to understand how ice cubes are formed. Electricity, which is mainly generated by steam power plant, requires the understanding of thermodynamics as well. Our aircraft, which also run by our turbine engine, requires understanding of thermodynamics too. So my main focus is to help mechanical engineering students and aerospace engineering students to further understand the concepts. So thermodynamics is talking about taking heat energy and convert it into useful energy, such as our steam power plant, where we take the useful heat energy from our steam to run the turbine and generate our electricity. Our gas turbine engine too is taking our heat from the heated air and spin the turbine so that the work from the turbine can run our compressor. Thermodynamics also helps us to understand how to use energy to transfer heat from one space to another, such as our refrigerator. We take a heat from the inside space of the refrigerator and rejected it to the environment. Now, let us focus on the equation. So the first law of thermodynamics tells us that the amount of heat transferred to the system, subtracting the amount of work done from the system, must be equals to the amount of energy changes from the system. For example, if your water is in your tank and there's some energy changes in the water, so that will help us determine amount of heat transfer from the water or the amount of work done from the water or both. If you are talking about a closed system, let's say water trapped in a tank where your tank can never be compressed or expand, then we can safely say that the amount of energy change will be the amount of internal energy changes from the water. So when we talk about internal energy, we talk about the kinetic theory of your water particles. So bear in mind that this energy will never be appearing out of nowhere or disappearing to outer space. It must be transformed from heat to work or work to heat. Now let's look at some important terms that will be useful for you when you're attempting your tutorials or when you're seeking for exams. So work done can be calculated by integrating PdV. This only happens when you have a isobaric problem and also a single state problem, which means to say when you are not looking at questions that having a change in state from liquid to gas or vice versa. For adiabatic, These questions tells us that you have a system where it is heavily insulated. This means that there will be no heat transfer. So anything that is changing inside the system will be purely on work done. If you have a question that tells you that it is an isothermal problem, then you have no change in temperature. When you have this kind of question, usually there is no internal energy change. So we can safely say that our heat transfer will be equal to our work done. But do take note, this only happens for single state, because when we have a change in state, usually it happens isothermally. So for this kind of problem, you can use this formula to determine the amount of work done or the amount of heat transfer for that system. For isobaric, this tells us that you have a constant pressure problem, like our piston cylinder here. So when there's heat transferred into our water, let's say, it will actually gives our water a lot of internal energy, and that helps it to expand, and this push up our piston. So for this kind of question, usually the work done can be determined by using P multiplying the change in volume. For isochoric, which is very seldom for engineering students to work on, is that when you have no change in volume. So this purely is a question, there is no work done. And when this happens, this tells us that your Q will be directly equals to the amount of energy change internally. So usually this question, we can simply use this formula to determine the amount of heat transfer, where Cv is your specific heat constant during constant volume. So if you are working on questions that is air, carbon monoxide, carbon dioxide, etc. for your state, you can use ideal gas equation to solve. When ideal gas equation is PV equals to mRT, where R is your gas constant. So when your R is 287, this means that your gas is purely a universal air. Else, you must use gas constant, that is for the respective gas. Do take note that temperature for this equation must be in Kelvin. So for any questions that is regarding state change, you have to use the thermodynamics table to determine the parameters you need for calculations. And do take note that you need at least 2 parameters to find out the necessary information you need. For instance, you might need either your pressure and your temperature, or your temperature and volume. So if you have only one information, usually you can determine the required information for your calculations. So I mentioned about enthalpy. Enthalpy is purely internal energy adding a constant pressure work that is happening in the surrounding of the system. So to give you some tips, if you have a closed tank, alright, a closed tank that's not going to be expanding or contracting, then use internal energy to solve your first law of thermodynamics. Else, if you have things that are flowing, like your refrigeration cycle, and your Rankine cycle, or even piston cylinder, then please use enthalpy to solve your problem. So these two formulas, mCv delta T and mCp delta T, can be used to find out your respective internal energy or enthalpy for your system when you have insufficient information And do take note, Cp is a specific heat capacity for constant pressure. Now let's look at the graphs that we will be using for thermodynamics. So in this graph, this is your PV graph. So it consists of pressure and volume. So do take note that your temperature line will be coming from the left to the right, where it comes from the high end. Then it will be an isothermal process inside your saturation line. Then it goes down after it passes saturation gas line. So this is a very important tool, I would say, that can help you understand where your state is and further elaborate your understanding. So in this case, when you see T2 and T1, usually the higher lines you have, this represents the higher temperature. Of course, in first law of thermodynamics, not just using PV, sometimes you have to use TV to elaborate your system. So TV consists of temperature and volume. So do take note the difference between a PV and a TV diagram, because your TV diagram, your pressure is coming from the low end of the left at the left side. Then after that you have an isothermal process. Once it passes out the saturated gas region, it will go further up. Likewise, the higher you draw the lines, the higher pressure you have. So do take note that this line represents a constant pressure. It is a single pressure. Similarly, this is a single temperature line. So for saturated lines, do take note that anything that belongs at the left side is a saturated liquid. Anything that is on the right is saturated gas. Whatever that you have after the saturated gas is superheated vapor. Whatever you have at the left just before your saturated liquid is compressed liquid. So in between will be a mixture of saturated liquid and gas. So one thing that to take note that if you're working on the gas question, do you need to draw the saturation line? So please do not draw this. Alright, if you are working on questions like carbon monoxide or air, because they are single state. There is no change in state. So do not draw a saturation line for a single state question, such as air or carbon monoxide. So let's work on an example. So if you guys want to work on this example yourself, you may pause the video. Okay, so this example consists of two tanks that's connected by a valve, where your tank A has 2 kg of carbon monoxide at 77 degrees Celsius and 0.7 bar. Tank B holds the same gas with 8 kg at 27 degrees Celsius and 1.2 bar. So when the valve is open, the gases are mixed together while receiving energy, which is heat, from the surrounding. So you are told to determine the final pressure and the amount of heat transfer, where your final equilibrium temperature is 42 degrees Celsius. And note that assumptions are needed. So this diagram shows you your system, where tank A has a temperature of 77 degrees Celsius, 0.7 bar pressure, and 2 kilogram mass. Tank B will have 27 degrees Celsius, 1.2 bar pressure, and 8 kilogram of mass. So after the valve is open, your temperature will be 42 degrees Celsius with heat entering the system. So what we can do is first do your assumptions. So some of the assumptions we can say is this is going to be a constant volume problem because there is not going to be having any expansion or contraction. And because we are working on carbon monoxide, it will be an ideal gas equation problem. And lastly, since since this is a constant volume, we can safely say that there is no work done. So, using ideal gas equation, we can determine our volume of A and B using the PV equals to MRT. We actually rearrange the equation to find out what is the volume of A. So with 2 kilogram, 296.84, which is the gas constant for carbon monoxide, we take 77 degrees Celsius and add 273 to turn it into Kelvin and divide it by 0.7 times 10 to the power 5. The reason I do that is because we are given the pressure in terms of bar. So we need to convert it into Pascal to solve this. So in the end, you should be having 2.9684 meter cube of carbon monoxide in tank A. Likewise for tank B, we are using the same formula, just at different values. We have 8 kilogram of carbon monoxide, same gas constant. For temperature, you take 27, adding 273, and we divide it by 1.2 multiplying 10 to the power 5. So you should be getting a volume of 5.9368 meter cube for tank B. So since this is a constant volume problem, after we open the valve, the volume should be the same. When I say the same, which means that for the volume of A, adding the volume of B will be constant. So this volume 8.9052 is the addition of VA and VB. Likewise for this 10 kilogram is the addition of 2 kilogram adding 8 kilogram. So the gas constant is the same. Our final temperature is 42 adding 273. So with all this information, we can safely find our pressure using the ideal gas equation. And we'll find out that your pressure is 105 kilopascal. So for part B, we need to determine the amount of heat transfer. Since for carbon monoxide, we can use the thermodynamics table to determine our internal energy. We can use the specific heat constant for constant volume to determine our change in internal energy. But because for tank B, you are actually gaining heat, while tank A is losing heat. So we need to subtract the change of heat transfer between the two tanks. So for this first line is actually the amount of heat transfer that is coming into tank B by taking 8 kilogram multiplying the CV of carbon monoxide, which is 0.744, and multiply the difference of temperature, which is 42 minus 27. And for our tank A, we can take 2 kilogram multiplying 0.744 and multiply the change in temperature, which is 77 minus 42. Well, if you want to do it the other way, you can actually write it as 42 minus 77. But do take note that for this sign, it will be a plus instead of a minus. So your final answer is supposed to be 37.2 kilojoules. Alright, so another example, we have a piston cylinder. So this piston cylinder contains 0.2 kilogram of water at 800 kilopascal pressure and 0.06 meter cube volume. So you have 200 kilojoules of heat transferred into the system, and the pressure is constant. So you have to determine the final temperature of the water and show the process in a TV diagram. You may pause this video to actually work this yourself before I show you my steps. So this is purely a piston cylinder problem where heat is transferred into the system, and it will expand our water and move the piston. So some assumptions is it is a constant pressure problem. So what we can find out is that you have a pressure that is going to be constant at 800 kilopascal. And you need to find the specific volume. When we talk about specific volume, you will take our volume of our state and divide the mass. So 0.06 divided by 0.2 gives us 0.3 meter cube per kilogram. So with these two information, we can use them to find out what we need in a thermodynamics table. And when you flip your thermodynamics table, you will find out that they are actually this water we are looking at is a superheated vapor. So when we are doing our extraction of data from our thermodynamics table, we have to run some interpolation because 0.3 in 800 kilopascal in your thermodynamics table is not really present there. So 0.3 happens to be in between 250 degrees Celsius and 300 degrees Celsius. Yeah, around between this range. So we have to determine our temperature based on interpolation, where you take the one that you have, which is 0.3, subtracting the lower end, dividing the higher end, subtracting the lower end. So likewise for your temperature, the one that you want to find, minus the lower end, dividing the higher end, minus the lower end. And I find out that the initial temperature will be 260.97 degrees Celsius. So the same thing, we can do this for finding our enthalpies. So with this information, your T1 and your volume, we can actually plot out your TV diagram. And please take note that since this is a superheated vapor, please draw it out of your saturated lines. As I mentioned, it is a superheated vapor. If you draw it at a saturated line, you'll be wrong because this is not a saturated vapor, it is a superheated vapor. So to determine the final temperature, since we know that the amount of heat transfer is 200 kilojoules, we can use the amount of energy change in the system to find. So the change in energy can be used as the change of enthalpies because there's a work done occurs in the system which is pushing the piston up. So internal energy plus the work is our enthalpy. So in this case, we can use 200 equals to 0.2 multiplying H2 minus our H1 that we found it in the previous slides. So by doing some calculations, you'll find out that H2 happens to be 3973.76 kilojoules per kilogram. So with this, we go back to our thermodynamics table, do some interpolation, and your final temperature will be 720.91 degrees Celsius. Alright, so do take note that when we are looking at thermodynamics table, interpolation is necessary sometimes. Alright, I hope you guys like my video. If you have any questions, do leave some comments below. And if you find my videos interesting, please like and subscribe to this channel. We hope to see you again to my next video or Dr. White's sharing. Alright, thank you.